Welcome to AI Unraveled, your special briefing on the real-world business impact of AI and advanced computing. Today, we dive into a tectonic shift in the strategic landscape of computation. Google has just announced what they call a verifiable quantum advantage with their latest Nature publication. This is not hype, this is a proven benchmark. The breakthrough, centered on a new algorithm called quantum echoes, is the first quantum experiment to measure a complex quantum observable that is mathematically beyond the simulation capacity of any known classical supercomputer. It's the sound of quantum chaos, and it validates the path to applications no current enterprise machine can touch. But first, a directive for AI infrastructure companies. Stop marketing to the general public. Your platform solves the hardest challenge in tech, getting secure, compliant AI into production at scale. But are you reaching the right 1%? AI Unraveled is the single destination for senior enterprise leaders, CTOs, VPs of Engineering, and MLOps heads who need production-ready solutions like yours. We have reserved a limited number of high-impact mid-roll ad spots. This is a direct line to your most valuable buyers. Secure your high-impact package immediately. Secure your mid-roll spot. Email us or check the show notes. This is a critical moment. For businesses, Quantum Echoes signals a clear, near-term reality. The path to applications in materials science, drug discovery, and advanced finance is accelerating. The question is no longer if quantum is real, but how your enterprise will build a strategy around this verifiable advantage. We break down the Nature publication and what this new family of observables means for your long-term infrastructure roadmap. Don't miss a second of this special edition. Please like and subscribe so you never miss a special briefing from AI Unraveled.
Okay, let's unpack this right away, because the news we've pulled from the source material, it's pretty startling. October 22nd, 2025, Google drops this announcement about a massive quantum computing breakthrough.
Yeah, and it really feels like it changes the game, doesn't it? The headline claim is just huge.
It is. Their quantum computer did some specific task, an estimated 13,000 times faster than the Frontier supercomputer. And Frontier is, one of the absolute top classical machines out there.
Right. But what's really significant, I think, beyond just the raw speed number is how they did it.
Yeah.
It's this combination of new hardware, the Willow quantum processor, and this really clever algorithm they published in Nature called quantum echoes.
Exactly. And that combination, that pairing, that's really our mission for this deep dive, isn't it? We're moving beyond just talking about speed, like abstract speed. This feels like a fundamental strategic shift in how quantum progress is measured, moving away from those, let's say, unverified claims of supremacy towards verifiable, useful science. Science you can actually check and trust.
That's the term they're using, verifiable quantum advantage. And it signals a new level of maturity for the whole field. It's about credibility now.
Credibility and scientific robustness.
Exactly. The goal is to show you, the listener, that the path forward isn't just faster, but it's actually correct. It's steering us towards solving real, complex scientific problems, not just, benchmark stunts.
Okay, so to really get why verification is suddenly front and center, we probably need to look back a bit. Remind folks about the 2019 Sycamore experiment. That was the big supremacy moment.
That's the one. Yeah, 2019, the 53-qubit Sycamore chip. That's when Google claimed quantum supremacy. The task back then was random circuit sampling, RCS.
Which was basically a problem designed just to be hard for classical computers, right?
Yeah.
Not necessarily useful.
Precisely. It was engineered for speed comparison. They claimed it would take a supercomputer 10,000 years to do what Sycamore did in about 200 seconds.
But the pushback was immediate, and that's really why this new 2025 announcement feels so, necessary.
Absolutely necessary. The critique back then was kind of two-pronged. First, IBM and others basically said, hold on, classical computers and algorithms get better too.
Right. They improved the classical methods.
Yeah, they argued the 10,000-year estimate was way off. Maybe it was more like 2.5 days. Still impressive, but not millennia.
Okay, but the second point was maybe even more fundamental.
I think so. For scientific confidence, it was crucial. The output of that RCS task. It was just a stream of random-looking numbers, bit strings.
And you couldn't easily check if they were the right random bit strings.
Exactly. There was no efficient way to definitively verify the answer. And, tackling abstract problems where you can't even be sure the answer is correct, well, that can erode trust pretty quickly.
So fast forward to 2025, and this announcement seems like a direct response. They're setting a new bar. Verifiable quantum advantage. What does that actually require? It needs two things. based on our sources.
Two essential pillars, yeah. One, the task still has to be demonstrably way too hard for classical machines. That's the advantage or speed part.
Still need the speed.
Still need the speed. But two, and this is the key shift, the result has to be efficiently verifiable. You need to be able to certify that the answer the quantum computer gives you is correct.
Makes sense. I mean, what's the point of a super fast answer if you don't know if it's right?
Exactly. There's that quote from one of the Google researchers, Tom O'Brien, that really nails it. If I can't prove to you that the data is correct, how can I do anything with it?
Yeah, that cuts right to it. So how does this quantum echoes experiment actually produce a verifiable result, unlike the old random bit strings?
Well, instead of just generating noise, this algorithm calculates something specific. It's a quantum expectation value derived from what's called an out-of-time autocorrelator, or OTOC.
OTSC. Okay, sounds complex.
It is, but the key thing is it's a deterministic, measurable physical quantity. It's not random. It's a specific value that relates to how information scrambles in a quantum system.
So it's repeatable and scientifically meaningful.
Precisely. That fundamentally changes the game. You can run the experiment again and get the same type of result, and that result tells you something about the physics.
Okay, let's switch gears to the hardware then. The Willow processor. This is the engine driving this. We're talking more qubits than Sycamore, right?
We are. Willow's a significant upgrade. It's a 105-qubit superconducting transmon chip. So yeah, nearly double the qubits compared to Sycamore's 53.
Double the qubits. But is it just about the number?
Not at all. Often the quality is more important than the quantity at this stage, and the quality has improved. They're reporting an average 2-qubit entangling gate fidelity of 99.88%.
99.88%. That sounds almost perfect. But hang on, if you're running a complex calculation, thousands, maybe millions of steps, doesn't even that tiny 0.12% error just snowball and wreck everything? How is that small fidelity bump a breakthrough?
That's a really critical question. And you're right, fidelity on its own isn't the whole story. Errors do compound incredibly fast.
So what else improved?
The real leap, arguably, is in the coherence time. This is basically how long the qubits can maintain their delicate quantum state before errors just overwhelm the calculation.
Okay.
The T1 coherence time on Willow reached almost 100 microseconds. Now, compare that to Sycamore, which was around 20 microseconds.
Wow. Okay, so that's roughly a 5-fold improvement.
Yeah, about 5 times longer. And that's huge. It means you have a much longer window to actually perform operations.
So better fidelity plus 5 times longer to actually compute. That means you can run circuits that are 5 times deeper, more complex, before the quantum state just dissolves into noise.
Exactly. More gates, more intricate calculations become possible within that coherence window. And this improved quality, this combination of fidelity and coherence, directly enabled another major milestone reported with Willow.
Ah, the error correction pit. Our sources highlighted this. Willow was the first chip to demonstrate below-threshold quantum error correction. What does that actually mean for, someone listening?
Okay, so the basic idea of quantum error correction is you use multiple physical qubits to represent a single, more robust logical qubit. The threshold is a theoretical point where adding more physical qubits actually starts reducing the error rate of the logical qubit instead of adding more noise.
So crossing that threshold is key.
It's vital. And Willow showed this principle in action. They demonstrated that when they scaled up the encoding, say from a 3x3 grid of physical qubits to a 7x7 grid, the error rate of the logical information they stored did decrease exponentially.
So it proves the underlying theory works on real hardware, that scaling up can suppress errors.
Precisely. It's a proof of principle that the path towards building a large, fault-tolerant machine, which absolutely needs error correction, is viable. It works.
Okay, that sounds like problem solved. Let's build the fault-tolerant machine. But I suspect there's a but coming, a reality check.
Yeah, there's always a but in quantum computing right now. While this is historic, Willow is still firmly in what we call the NI-skew era.
Noisy intermediate scale quantum.
Right. The logical error rates they achieved while demonstrating the principle were around 0.14% per cycle. Still quite high.
How high compared to what we need?
Well, the target for running really powerful algorithms, like Shor's algorithm for breaking encryption, is believed to be an error rate around 10 to the minus 6, so 0.00001%.
Okay, so 0.14% versus 0.00001%.
That's roughly 1,000 times higher, orders of magnitude away. So huge progress on the principle, but the actual error rates are still far too high for fault-tolerant computing.
Got it. So the hardware's improving, error correction concepts are being validated, but noise is still a major challenge. which I guess puts even more pressure on the algorithms to be incredibly clever, right? Like quantum echoes.
Exactly. You need algorithms that can extract useful information despite the noise.
So let's dig into quantum echoes. You mentioned it measures OTOCs, out-of-time order correlators. Remind us what those tell us again.
OTOCs are basically a mathematical probe for how information spreads or scrambles in a complex quantum system. Think of it like the quantum version of the butterfly effect.
How quickly a tiny disturbance ripples outwards and affects everything.
Yeah, that's a good way to think about it. It measures the onset of quantum chaos.
Okay, chaos sounds like the enemy of computation. How does this echoes technique manage to get a clean, verifiable signal out of quantum chaos? That seems counterintuitive.
It does, but the technique is really quite ingenious. It sort of turns the chaos into a tool. It works in 4 main steps.
Okay, walk us through it.
First, you let the quantum system evolve forward in time naturally. Things get scrambled, chaotic.
Step 1, scramble. Got it.
Step 2, you introduce a very small, controlled perturbation, a little poke to the system.
Step 2, poke the chaos.
Yeah. Then step 3, and this is the clever part,
Yeah.
you evolve the system backwards in time. Essentially, you try to run the quantum movie in reverse.
Reverse the scrambling. Okay.
Finally, step 4, you measure the final state.
So how does running it backwards help? What's the echo?
Well, think about it. If you just ran it forward and then perfectly backward without the poke, you should ideally end up back where you started. The backward evolution cancels the forward one.
Right, a perfect echo would mean no change.
Exactly. But with that tiny perturbation from step 2, the backward evolution doesn't perfectly cancel the forward one anymore. There's a mismatch.
Because the poke changed things slightly.
Precisely. And here's the crucial physics.
Hmm.
The forward and backward evolutions interfere with each other quantum mechanically. It's called many-body interference. This interference pattern actually amplifies the effect of that tiny perturbation relative to the background chaos.
So the chaos partially cancels itself out, making the small signal easier to see.
That's the essence of it. It allows the signal related to the OTOC to decay much more slowly than you'd expect, making it measurable even on a noisy processor like Willow. It cleverly uses quantum interference to isolate the signal you care about.
And that reliance on quantum interference, that's the wall classical computers hit, right? That's why they can't keep up.
That's the fundamental reason. Classical simulations track probabilities, always positive numbers. But quantum mechanics runs on probability amplitudes, which are complex numbers. They can be positive, negative, imaginary. They behave like waves.
Waves can interfere, cancel each other out.
Exactly. Classical computers simulating these systems run into what's called the sign problem. Trying to average out vast numbers of positive and negative pathways leads to catastrophic cancellation errors. They just can't efficiently handle that quantum interference.
And the scale difference is just mind-boggling. The sources mention simulating just 65 qubits for this experiment.
Yeah, an exact classical simulation would mean storing and manipulating a vector with 2 to the power of 65 complex numbers. That's astronomical, way beyond any current or even foreseeable classical machine.
Which leads back to the performance claim.
Right. That's how they estimate that calculating just a single data point for this specific OTOC experiment would take Frontier, the supercomputer, something like 3.2 years.
3 years
versus hours on Willow. And because the result is a verifiable physical quantity, you can trust that speed gap. That's the 13,000-fold advantage, and it's verifiable.
Okay, massive speed up, verifiable result, check, check. Now, the crucial next step, making it useful. They didn't just run an abstract calculation. They applied this to something, right? A real physical problem.
They did. The first application demonstrated was something called Hamiltonian learning.
The Hamiltonian, that's like the fundamental rule book for a quantum system. It's energy and interactions.
Exactly. If you can figure out the Hamiltonian, you understand the system's behavior. The idea here is that the OTOC signal, how that information scrambles, acts like a unique fingerprint for the system's dynamics.
So you run the quantum simulation, get the OTOC fingerprint, and match it to a real system to deduce its rules.
That's the core concept. By measuring these OTOCs, you learn about the underlying interactions described by the Hamiltonian.
And the specific application they used as a test case was related to NMR nuclear magnetic resonance.
Yeah, NMR spectroscopy. It's a standard technique, often used in chemistry and biology, to figure out the 3D structure of molecules.
So what did the quantum echoes algorithm do for NMR in this proof of concept?
They used the quantum simulation to effectively probe the magnetic interactions between atoms within a molecule. The key finding was that the quantum simulation could detect interactions between atoms that were further apart than what standard NMR techniques can typically resolve.
Ah, so it's like having a ruler that can measure longer distances within the molecule.
That's the analogy they use, yeah. A longer molecular ruler.
Mm,
It potentially allows you to see finer details of molecular geometry over greater atomic separations.
that sounds potentially very useful. But we need that critical clarification again. This specific NMR experiment on these small molecules. Was it actually beyond what classical computers could do?
No, it wasn't. For the small molecules they tested, a classical computer could have done the simulation.
So why do it then?
Because this is arguably the most vital step for building trust and moving forward. Think of it as the hello world for this whole approach.
The first basic program you run to make sure everything works?
Exactly. It proves that the entire pipeline, the quantum echoes algorithm running on the noisy Willow hardware, interfacing with the control systems, can correctly solve a known problem where we already know the answer, or can calculate it classically.
So it validates the tool.
It validates the tool. It establishes the baseline confidence needed before you turn this tool loose on problems that are genuinely too hard for any classical machine. You first show it works where you can check it.
That makes a lot of sense. Build the confidence first. So with that confidence hopefully established, where does this capability point us? What are the big future applications everyone's excited about?
Well, two fields consistently come up: drug discovery and material science.
Let's take drug discovery first. What's the bottleneck that quantum computers could break?
Simulating molecules accurately requires quantum mechanics, especially understanding how drugs bind to target proteins. Classical computers really struggle to do this accurately for large, complex molecules. The computational cost just explodes.
So quantum computers could model those interactions precisely.
That's the hope. Predict binding affinity more accurately, model how proteins fold, maybe even forecast toxicity or side effects much earlier in the drug development process, saving time and money.
And there's often talk about synergy with AI here too, right?
Absolutely. One major challenge for AI and drug discovery is getting enough high-quality training data. Quantum computers could potentially generate incredibly accurate simulation data about molecular interactions data that's basically impossible to get classically.
So the quantum computer generates perfect training data for the AI.
That's the idea. Feed that gold standard data into specialized AI models to accelerate the search for new drug candidates. It overcomes a key data limitation for classical AI.
Okay, and the other big area was materials science, designing new materials.
Right. Things like searching for high-temperature superconductors, better catalysts for industry, improved battery materials. Again, the challenge is classical computers hitting a wall when trying to solve the fundamental equation of quantum mechanics, the Schrödinger equation for complex materials.
It just gets exponentially harder.
Exponentially harder. Quantum computers, because they operate on quantum principles inherently, are naturally suited to simulating the electronic structure of these materials. The dream is to move from trial and error discovery to rational, targeted design based on accurate simulations.
It all sounds incredibly promising, a potential revolution in science and technology. But let's bring it back to that reality check one last time. Google has its own roadmap with milestones. Where does this achievement fit, and how far is the road ahead?
Yeah, they laid out a 6-milestone plan. Milestone 1 was achieving that early supremacy demonstration. Milestone 2 was demonstrating the prototype error correction, which they essentially achieved with Willow.
Okay, so we're past M1 and M2. What's next?
The current big goal is Milestone 3, creating a robust, long-lived logical qubit. This is a much higher bar.
What does that entail?
The target specs are something like encoding one logical qubit, using around 1,000 physical qubits, having it survive for maybe 1 million computational steps, and achieving that incredibly low error rate we talked about, around 10 to 6, 1 in a million.
And we're still facing that 1,000-fold gap in error rates from what Willow showed, even with the breakthrough.
We are. That gap remains the major hurdle. Closing it requires significant improvements in qubit quality, coherence, gate fidelity, and the engineering of the error correction codes themselves.
And external experts echo this caution, right? It's progress, but the mountain is still steep.
Definitely. Professor Winfried Hensinger, for example, acknowledged this is convincing proof of increasing power, but pointed out it addresses a relatively narrow scientific problem. True fault-tolerant machines, the kind needed for the really big applications, likely require hundreds of thousands, maybe millions of physical qubits.
And the engineering challenges there.
Yeah.
Cooling, control.
Immense, especially maintaining the necessary cryogenic temperatures and stability at that scale. It's a monumental engineering task alongside the fundamental physics challenges.
Okay, so let's try to sum up the big picture here. The quantum echoes breakthrough, powered by the Willow chip, really marks a shift, doesn't it? Moving away from just abstract speed contests
Right.
towards a scientifically solid methodology. Verifiable quantum advantage, speed plus correctness you can trust.
I think that's the key takeaway. It gives the field a clear direction and, crucially, a verifiable method for using these early quantum computers as actual scientific instruments. It starts to answer not just if they're faster, but how we can reliably use them to probe nature.
It sets a standard for meaningful progress. Okay, so here's a final thought for you, our listeners, to chew on, building on all this. We've heard how this quantum echoes technique can cleverly use quantum chaos, turn it from a bug into a feature, making faint signals measurable. It acted like a longer molecular ruler in that small NMR test case. So the question is, what currently impenetrable, massive, complex quantum system, maybe in fundamental biology, maybe in the dynamics of exotic materials, or even high-energy physics, what system will be the first to truly reveal its secrets when we point this new, verifiable quantum instrument at it? What grand scientific mystery will the first reliable quantum echo finally help us solve?
That's it for today's deep dive. We hope you walked away with actionable insights for your enterprise strategy. Before you go, let me remind you of the unparalleled value of this platform. AI Unraveled delivers deep, uncompromised technical insight that keeps our audience, senior enterprise leaders, tuned in to the very last minute. That sustained attention is the best place for your ad. This is your opportunity for a direct line to your most valuable buyers, the CTOs, VPs of Engineering, and MLOps heads who sign off on high-stakes infrastructure. Stop wasting budget on general marketing noise. Secure your high-impact premium ad campaign right here. Email us today to reserve your mid-roll package, info@djamgatech.com. Thank you for listening to AI Unraveled. We'll be back tomorrow with more.